Hey everyone, Michael here, and today we're going to be talking about the wonders of thermodynamics. But what is thermodynamics and what does it have to do with us? Well, in the essence of thermodynamics, there are technically 4 laws, but one is an absolute law, so it's called the zeroth law, which is the transitive property which is used to show what happens when two systems are in thermal equilibriums. But what is a thermal equilibrium? Well, a thermal equilibrium is basically when there's no transfer of heat between two systems with the same temperature. So if you were to add boiling water to boiling water, it wouldn't double the temperature, but it will remain the same because they're at the same temperature or thermal equilibrium. This goes on to other systems. Systems of higher temperatures tend to transfer to ones of lower temperature. Temperature can also be seen as the amount of kinetic energy a substance or object has. So more kinetic energy means higher temperature and the more molecules start to move. So when two systems interact, one being hotter than the other, the system transfers into the lower system. It is trying to evenly distribute the amount of kinetic energy within the heat transfer. When the energy is added to a substance, the temperature will change by a certain amount. The relationship between heat and temperature is different for every material, and the specific heat capacity is the value that describes how they relate this way. This is why we use the formula Q equals mc times delta T. But we do not use this for the phase change because delta T remains the same during transitions. Instead, we use LF or LV. The first law of thermodynamics is the conservation of energy, which states that energy cannot be created or destroyed but can alter or change form. The conservation of energy can relate to many things we studied, like the red hot nickel ball melting through ice or the immersion heater lab we did in class. Now, how exactly do either of these relate to the conservation of energy? Well, the red hot ball can be seen going through a huge block of ice. When this happens, water and vapor start to come off the ice. This is due to the heat transfer between the two objects while the ice is melting and sublimating. The red hot ball then starts to lose its color due to the hyperactive molecules in the metal ball starting to vibrate less and cool due to the ice around it. And on the microscale, the ice is using the heat to break its bonds, altering its state of matter. This is now changing the physical features of both substances. The use of energy to break and change bonds can relate back to a previous unit in which we learned that we need work to do work on an object. So in this case, energy put into the object is then needed to be able to break and change the intermolecular forces in another object. The lab with the immersion heater has to do with the changes and properties of water. In the lab, we place a certain amount of ice cubes to water in a cup. We then place the immersion heater lab within the cup. In the first 20 seconds of the heater being placed within the water remained at 1 degree Celsius. This is because of the potential energy being used in place. This is because the heat emitting from the heater is used to break and change the bonds rather than speed up the molecules. This is why it's potential energy and not kinetic energy, because the temperature is not rising. If it was, it would indicate that the molecules in the water were moving faster, and when this happens, it is kinetic energy, because there is a change in temperature and there's going to be a change in matter. Within the lab, the ice melted and the water vaporized correspondingly. The temperature would also remain the same when the water vapor condenses and the water freezes to ice. To calculate the energy needed to change the phase of a certain substance, we then need to use the formula Q equals mL, in which m is the mass and L is the latent heat for specific substances in specific transitions, between solid and liquid, between liquid and vapor. The second law of thermodynamics is that entropy in the universe is always increasing. Entropy has to do with the order of chaos within the universe and different types of driving forces, negative delta H and positive delta S. There are also 2 different types of delta S driving force, positive S and negative S. The same goes for delta H. These driving forces closely correlate with heat. Because of this heat correlation, it is possible to identify whether the reaction is exo or endothermic. With endo and exothermic reactions, breaking bonds need energy input, while forming them needs energy output. If the energy put out is less than the energy put in, it is endothermic because it uses more energy in the process. If a reaction is exothermic, it is because the overall process gives out more energy. To compare the heat input and output, we need to use the formula delta H equals sum of all products minus sum of all reactants. This can be seen because objects with higher physical potential energy are less stable with those of low potential energy. Those with high potential energy give off their energy in form of heat. This is because reactants tend to transform in more chaotic molecules. There are also differences in reactions between the driving forces. For example, when delta H is negative and delta S is positive, it's always gonna happen. When delta H is positive and delta S is negative, it never happens. When delta H and delta S are both negative or positive, the reaction sometimes happens. Well, now we know how the reactions occur, we now have to determine whether or not the reaction is spontaneous. We then use Gibbs free energy. This equation, delta G equals delta H minus T delta S, shows whether or not it is spontaneous. When Gibbs free energy is negative, the reaction is spontaneous. When it is positive, the reaction is non-spontaneous. We finally come to the third law of thermodynamics, which is that no system can reach absolute zero. This is because no system can be completely isolated. The reason absolute zero is impossible to reach is because molecules are constantly moving due to quantum mechanics. Now, what we can take away from this is that thermodynamics takes a huge place in our everyday life. This can be seen anywhere from heaters and AC to explosives that our military uses, and can help us better understand forces within the universe.